In the last lecture, we saw lots of examples of computing ideal class groups of imaginary quadratic field using the bijection with equivalence classes of binary quadratic forms of the given discriminant equal to the discriminant of the field. And I stated a theorem that we used in one or two of these examples, and I will recall that theorem today and we will give a proof of this theorem today. Okay, so that is our aim. So, let K over Q be an imaginary quadratic field of discriminant d, which is dk. Okay. Let T be the number of distinct prime factors of dk. So, d, right. Then the number of elements in ideal class group of K of exact order 2 is 2 to the t minus 1 minus 1. Okay. So, if there are two distinct prime factors for the discriminant, then there will be exactly one element of order 2. If there are three distinct prime factors of the discriminant, then there will be exactly 3 elements of order 2 and so on and so forth. Okay. So, here is a proof, right. Okay. So, the reason why we can analyze the number of elements of order 2 as opposed to some other order is the following. So, you observe that for any integral ideal, for any integral, it need not be integral, but for any, let me just say ideal non-zero, A inside OK, A times sigma A, this is equal to the ideal generated by norm of A, right. And whenever I write norm, I always mean norm from K to Q in all this, in the previous lectures, in this lecture, etc. Okay. Unless there is some ambiguity, I will not write down K over Q. So, you see that A times sigma A is a principal ideal, right, which means that the ideal class of A, the class of A is inverse of the class of sigma A inside the ideal class group, right. So, we denote class of A in the ideal class group of K by square bracket A. So, that will denote the equivalence classes of ideals. So, what I have said is this is equal to sigma A inverse, right. Now, what happens when an element has order 2? So, this thing has order 1 or 2 if and only if it is equal to its own inverse. Sorry, if it is this is not what I wanted. So, an element has order 1 or 2 if the inverse of that element is the element itself, right. So, of course, that happens for the identity element, but it also happens for order 2 elements, that is why I said 1 or 2, right. And so, sigma A square bracket A has order 1 or 2 if and only if this thing and sigma A they denote the same ideal class in the ideal class group of K, right. Okay. So, so that is kind of purely on the side of ideal class groups. I have not used anything about quadratic forms yet. So, I need to say I need to now use the fact that there is a bijection between ideal class group and binary quadratic forms of discriminant dk. Okay. So, how did we get that bijection? So, if alpha 1 alpha 2 is a z basis of A such that imaginary part of alpha 2 by alpha 1 is bigger than 0, then we have a z basis of sigma A as well. Then the z then so the sigma alpha 1 and sigma alpha 2 is a z basis of sigma A. So, that is clear that if you have a z basis of A, then you can just transform the basis under sigma and you get a z basis of sigma A. What is the imaginary part of sigma alpha 2 by sigma alpha 1? This is equal to the imaginary part of sigma alpha 2 by alpha 1, and sigma is like complex conjugation. So, if you apply complex conjugation to a complex number with positive imaginary part, then it becomes negative, right. So, it is less than 0. So, that is not quite what we want, and so there is a very easy remedy for it. Notice that sigma alpha 1 and minus sigma alpha 2 is a z basis of sigma A, and imaginary part of minus sigma alpha 2 by sigma alpha 1 is bigger than 0. So, the z basis that we are going to use for sigma A is not sigma alpha 1 sigma alpha 2, but sigma alpha 1 and minus sigma alpha 2. Okay. Now, let us say that with this choice of basis with alpha 1 alpha 2 and A, let ax squared plus bxy plus cy squared be the reduced binary quadratic form associated to A, right, to this class of A. Let me write it this way. Then yeah, so okay, let me do it the following way. If A is same as sigma A, then the reduced binary quadratic form associated to sigma A is also ax squared plus bxy plus cy squared, right. Okay. But what is the, but if you directly associate, but if we associate binary quadratic form to sigma A using the basis sigma alpha 1 and minus sigma alpha 2, then we get ax squared minus bxy plus cy squared, right, because the only quantity where this change of sign is relevant is b, right. And so what we need, and this is also reduced. So if ax squared minus bxy plus, sorry, plus this thing is reduced, then so is ax squared minus bxy plus cy squared. Okay. All right. So, going back to our statement, this thing is equal to sigma a if and only if ax squared minus bxy plus cy squared is equivalent to, but they are both reduced, right. So, is equal to ax squared plus here and then minus here, it does not matter where I put the plus and minus, it is equivalent to this, right. So, this happens, so this is if and only if they are of the form a x squared plus cy squared. So, b is equal to 0, or it is of the form ax squared plus minus ax y plus cy squared, or it is of the form, so b is whatever it is and a and c are equal. In each of these cases we can choose a good representative for a, right. So, a's are given ideal, we can't do much about it, but we can now change it within its class. So, in each of these cases we can take a to be the ideal generated by a and a beta, where a beta square plus b beta plus c equal to 0. So, beta is a is any number with which satisfies this, right, and then sigma of a, right, and of course we choose beta so that imaginary part of beta is bigger than 0. There are two betas which satisfy this equation, one of them will have imaginary part bigger than 0, the other one will have imaginary part less than 0, and so this is the one we choose, minus a sigma beta. Right. So, we can change our a within its class and assume that our a is like this, right. Okay. All right. So, in this case we see that a is equal, the class of a is equal to class of sigma a if and only if a is equal to sigma a, right. So, as ideals, these are as ideals. So, not only that their class are same, but with this good choice of a representative in each class, we see that the ideals themselves are same. What does that mean? If you have understood the course up to now and how the prime decomposition etc. works, this means if and only if the only primes dividing a are prime ideals. So, primes means prime ideal. So, let me write it explicitly here, the only prime ideals dividing a are ramified primes or inert primes. So, things that are already coming from primes of Q. We can ignore inert primes, we can divide out by inert primes. So, those really do not matter, the only primes that matter are ramified primes, right. So, a class in the ideal class group has order 1 or 2 if and only if we can choose an integral representative for that class which is divisible only by ramified primes. Okay. So, let me say what we have proven up to now. So, a class in CLK has order 1 or 2 if and only if we can choose a representative A such that A is divisible only by ramified primes in K over Q. So, primes that ramify in K over Q. Now, how many primes ramify in K over Q? Right. So, what are the primes that ramify? The primes P in Z that ramify in K. These are precisely P dividing D, right. And so, there are hence there are precisely T rational primes that ramify in K, right. And so, we can, so there are 2 to the power T possible combinations of these primes, right. I mean, over every ramified prime there is exactly one prime in K, and whether or not you choose that prime when you form the ideal A tells you that there are 2 to the A possible classes. So, there are 2 to the T distinct ideals of K divisible by ramified primes only. Okay. So, there are 2 to the T possible classes that have order 1 or 2. So, there are at most 2 to the T classes in CLK with order 1 or 2, right. Why not exactly 2 to the T? Well, some of these classes could be the same, right. They could match up, or some of these classes could have order 1, right. More than one of these classes could have order 1. If you do not include any prime, if you take the trivial ideal which is one of these 2 to the T possibilities, then of course it will have order 1, right. But there could be other things which have order 1 as well, and so we have to find out exactly how many have order 1. Okay. All right. So, when does something have order 1? So, we have to find which of these 2 to the T ideals has order 1 in CLK. What does that mean? What does order 1 mean? Order 1 means that the ideal is a principal ideal, right. So, we have to find out which of these ideals is a principal ideal, right. So, say let A be a principal ideal which is of the form alpha belongs to OK, right. But what is OK? OK was the ring of integers inside K, and so a way to write this is yes. So, this one way to write this, and you can take this as an exercise if you like, this is half of x plus y square root of d such that 1 by 4 x square minus dy square is in z. So, remember that right, I mean why is this true? Well, so this all depends on what the parity of d is. If d is odd, then it's d is 1 mod 4 and your k is square root of q square root of d, in which case you know that 1 and 1 plus square root of d by 2 is a basis, and so you can write everything in this way. Or d is even, so it is divisible by 4, in which case both x and y have to be even here, and you get that k is square root of OK is z square root of d by 4, right. So, okay. So, in any case what this means is that norm of alpha, this is equal to half x plus y square root of d times half x minus y square root of d. This is so here x and y are in z, of course, and so you get 1 by 4 x square minus dy square, right. Okay. And so norm of A is the ideal generated by 1 by 4 x square minus dy square, and I know that this divides 1 by 4 x square minus dy square, it divides d, right. So, I want to find out solutions of all these things, right. So, I want to find out what are the solutions for how many x and y I can find so that I get this. So, we want to find, x and y in z such that 1 by 4 x square minus dy square divides d. Okay. So, you write x square minus dy square is equal to we can always change the right, we can always change the sign and say that this is minus 4 d by r, so that we have positive for some r dividing d, so that we have positive number on the right hand side, right. D is negative, and so minus 4 d will be positive, all right. Yes, so now we need to find solutions of these things, but you see that also x square minus dy square is also positive, okay, because d is negative, and so this gives a very tight bound on what y is. So, y mod y has to be less than or equal to 2. Right. So, minus 2 is less than or equal to y is less than or equal to 2, because if y is bigger than 2, then minus dy square will be bigger than minus 4 d, which is already the quantity on the left hand side, right hand side. Okay. And so, what we can do is we can just take cases one by one, right, and so we can take x to be so we can take y to be 0, then what happens is x square is minus 4 d by r, right, and so the only solution for this is, so remember that d is I mean, so one thing is that x square x cannot be a prime number, because we have already divided out by the ramified, not the ramified, but inert primes, right. So this means that the only solution is so in this case the only solution is x is equal to plus or minus 1 and d is equal to minus 1, yeah, not minus 1 but minus 4, right. Okay. So that is when you adjoin square root of minus 1, or you could have y is yeah, you could have y is plus or minus 1, then x has to be plus minus 1 as well, and d is equal to minus 3, right. So you get 1 minus 3, so 4, and d is minus 3 and r is 3, or you could have x is equal to plus minus 3 and d is equal to minus 3. So, I think in this case you get 9 minus minus 3, so minus 12 and r is 1. So, in this case r is 3 and in this case r is 1, right. Or you could have y is equal to plus minus 2, in which case x is equal to 0, because again otherwise you can't have x squared minus dy squared equal to 4d by r, and in this case d can be whatever it can be, right. It is there is no restriction on d as such. So, the only yeah, so the upshot of all this, and I do not want to go case by case, but let me write upshot of all this, and you can take it as a sort of exercise of putting everything together. There are exactly 2 principal ideals in amongst those divisible by ramified primes, and what are these? Namely the trivial ideal and the ideal generated by square root of d, right. And so, out of the 2 to the t ideals, there are these 2 which are principal ideals, and you see there is for every non principal ideal there is also another ideal whose product gives you square root of d. So, what you get? So, hence there are 2 to the t by 2 minus 1 ideal classes of order 2, and what is this? This is 2 to the t minus 1 minus 1, which is exactly what we wanted, right. Okay. So, that proves the theorem, and as I said, this theorem is quite useful because the bijection between ideal class group and binary quadratic form, it just tells you about the order of the ideal class group, but sometimes using this theorem we can also tell about the structure of the class group, and later on we will do examples of computing class group using Minkowski bound, and there you will see that some of the examples that we did using binary quadratic forms, examples with relatively large discriminant, it can become very tricky if you want to use Minkowski bounds only. So, next time we will look at number fields other than quadratic fields. So, up to now we looked at explicit things about binary about quadratic fields. Next time we will look at cubic fields and biquadratic fields. Thank you.